Hello, class. I'm hopeful that, yeah, there, my microphone's a little bit better now. I thought that I would do this lecture on, I say projectile motion, but it's not really, it's really kinematics and curvilinear motion and stuff like that. Although on this first one, we're going to sort of approach this as a one-dimensional thing, and then problem, and then turn it into a two-dimensional problem. That's what I'm going to do. Have a little sip of coffee, and let's begin. Now, here's the statement of the problem. I'm actually going to put the problem over here. We've got a cliff, and we've got a guy. Let's just put someone here, and he's throwing a ball upwards from this cliff, right at the top of the cliff. Let's say that he has the ball right here, and he's going to throw the ball up, and the ball is going to go up a certain distance, right? And then the ball is going to come down again. All right, let's say that, in fact, let me look at the thing for a second. I just want to do 18, yeah. So let's say that the ground is right here, and that this distance here is 18 meters, right? 18 meters, so really 18 meters, that's about 50 feet, isn't it? He's going to throw that ball up with an initial velocity of 12 meters per second. Now we know that the acceleration is going to be minus 9.81 meters per second squared, right? That's not a great pen. Anyway, just going to have to live with it. So now we know that's 18 meters. And so that really tells us, because we want to find out all about this, we want to find out how high is this going to go, right? How high above the surface of the ground is this going to go before it crashes down to the ground? This would be 0 meters, right? And this would be 18 meters. So how high is this going to go entirely from the bottom here? How long is that going to take? Right? How long is it going to take to throw it all the way up here and then for it to stop? Because let's face it, up here, Vy equals 0, doesn't it? Right, in the y direction, there's not going to be any velocity anymore. And in fact, the way that I've set the problem up, we're not even worrying about any velocity here in the x direction. Maybe it's 1 meter per or one centimeter per minute, just enough for it to get off the edge of the cliff here, for where he throws it. So I want to find out two T's. I want to find out the time that it takes for it to get to the highest point, and then I want to find out the total time too. Right, so I want to find out all of those things. And how do I do that? Well, I've got to do some kinematic analysis on the problem, don't I? And I have to use my equations that I've come up with before, my equations of motion, and in two ways. In fact, let's write down the equations of motion. So we know that S sub F is going to be S sub O plus V0 times T plus 1/2 AT squared, right? And we also know that V final equals V initial plus acceleration times time, right? So we've got those two equations, and then of course we've got that third equation, but let's not even worry about that right now. Okay, So we know a couple things. We know that the final velocity in the y direction is going to be 0, right? So we can figure out how long is it going to take to go from here to here. Let's call this point A, and we'll call this B, and I'll call this C. So what is the time from A to B, right? What is the time from A to B? Can't we use this first equation that we've got here? Because if we know what the original velocity was, and we know what the final velocity was, and we know what the deceleration was, and that should be pretty easy, right, to get the time. So I've got V sub F minus V sub O divided by the acceleration. Well, let's see, final, and this would be in the y direction, right? So the final velocity in the y direction is 0 meters per second, minus the initial velocity, which is 12 meters per second. Did I start that? Yes, I did. Okay, good. And then divided by minus 9.81 meters per second squared. Does everyone see we got a minus in both of those two, points here? I've got minus 12 meters per second and minus 9.81 meters per second squared. So what that tells us is that the time that it takes to get to that high point is going to be 1.22 seconds. 1.22 seconds. How high is that highest point? And really what we're going to be finding out is, well, let's just write out the equation. So the final height, I'm going to go with the final height above this, which is going to be, or the final distance, which is going to be the height up here, is going to be the 18 meters that we started with, plus the original velocity, 12 meters per second, right? Times the time. Now we know the time to get to that high point from A to B, right? So this is really the distance from A to B, all right? 12 meters per second, 1.22 seconds, minus 1/2 times 9.81 meters per second squared, times the time, 1.22 seconds, and that squared. Let's take our separator pen. I use the red pen for everything. And just put a line through here so that we know which equation belongs to which. Sorry about that. All right, that's just my little separator line. So what we do is we can get a distance. So my final height is going to be 39.94 meters. And that's the height off this. So that's what h is. That's what h is. So that's one of the things that we wanted to find out. Boy, that didn't work out well. I went across through the other one. But that's 1.22 seconds. And that was something, the time that it's going to take for us to go from A to B. And let me just write that time A to B. And I can circle that one too. There we go. All right, so we've got really the time to get to the highest point already there. We've got the actual height above the datum plane. So this is equal to 39.94, but remember it's got 18 meters already, so it's only 21.94 above. So if I had to look at this distance here, that would be 21.94 meters, right? But the total distance is 39.94. It's because I added the 18 meters in there to begin with. I hope everybody sees that. Okay. Okay, so we've learned two things about this problem, but we've got a lot more that we want to learn. Now, we could just analyze this. We could say, okay, well, that's 0, and then how fast is it going to be going when it actually hits the ground there? You know, that's that would be interesting. We could always figure out what the velocity is when that were to hit the ground. But I want to find out how long is it going to take for that to hit the ground, right? Because we're throwing it up and it's coming back down. So what is that time to hit the ground? Well, we know that the final distance above the ground is going to be 0 meters, right? We know the original distance above the ground is 18 meters. We know that the velocity up is 12 meters per second, and we want to find out how long that's going to take. We also know, right, that's a t, by the way. We also know that it's 1/2, right, a t squared. So isn't that really a divided by 2 times t squared? I'm just going to put parentheses around that so that you know what's going on in your notes. And of course, well, let me take my correct type. In fact, I can actually save myself a little time right here because that's really a minus g, isn't it? I'm going to put g in there. Minus g t squared. So we know a couple things now. We've got this quadratic here, and we know what g is. G, of course, is 9.81 meters per second squared. All right. Now, what I want to do is I want to take this quadratic and look at the 3 main components, coefficients inside that quadratic. So for A, I've got g divided by 2, or 4.905, right? For B, I have 12. For C, I have 18. So let's actually solve for this quadratic. So T is going to be minus B plus or minus the square root of getting ahead of myself, of B squared minus 4AC, sorry, B squared minus 4AC, all divided by 2A, right? So let's just do this. So I've got minus and then B12 plus or minus the square root of 144 minus 4 times 4.95, 905, I'm sorry, 4.905 times 18, right? And that whole thing divided by 9.81. Now, I'm just going to simplify this a little bit for you. 144 minus 4 times, let me just give you a value for that so that we can analyze this together. 4 times 4.905 times 18 is 356.4. 356.4. So I've got T equals minus 12 plus or minus the square root of 144 minus 356. Oops, sorry, that's a minus 9.81. Minus 356.4, but I'll just leave the 356 there for now. Divided by minus 9.81. That does not look too good. What have I done? -4. Oh, that's supposed to be a plus, isn't it? Minus, because that this is minus 4 point. Sorry, that's a minus 4.9. So let's put the minus in there, and that of course makes that a plus, and that makes that a minus. So thank God. So 144 plus 356. That gives me 500. So minus 12, t equals minus 12 plus or minus the square root of 500. Who would have thought? That's 22.37. 22.37 divided by minus 9.81. All right, so let's figure out what our two roots of that equation are. I've got minus 12 minus 22.37. That gives me minus 34.37, right? Divided by 9.81, actually minus 9.81. And that gives me 3.5 seconds. Or, now let's do it the other way. I've got minus 12 plus 22.37, right? And that gives me 10.37. If I divide that by 9.81, that gives me t equals minus 1.057 seconds. So we've got two answers now, 3.5 seconds and minus 1.05 seconds. Which one of those is correct? That's what I wanted to point out to you. That's why I wanted to bring this problem up. This is a very interesting problem in rectilinear motion and kinematic motion, is because you say to yourself, well, obviously minus 1.057 seconds is incorrect because you'd have to go back in time, right? You'd have to go back in time. Here's what I want you to see. This right here, I'm going to just draw it in orange. I hope everybody can see that in orange. That is the 3.5 seconds. Now, what's the minus 1.0 seconds? 1.057 seconds. That would be if instead of throwing it up and going the whole distance, he was just to drop it off the edge of the cliff, right? Drop it off the edge of the cliff just to go those 18 meters. Just to go those 18 meters, if he dropped it, it would take 1.5057 seconds to get to the ground. If he dropped it from that location, A, it would take 1.057 seconds to get to the ground. That's what the minus means, right? It's not an imaginary number or anything. It's not a number that doesn't mean anything. It means something. It really does mean something. It's not, you know, and I'm not even an imaginary number, right? That's a minus. So that's what it's telling us. If I were to, instead of throwing it up in the air, I turned around. Now, excuse me, I'm not dropping it. It would take 1.057 seconds if I threw it down at that velocity, right? So in other words, I took the 12, if I took the 12 meters per second and threw it down at 12 meters per second, instead of throwing it up, it would take 1.057 seconds to get down to the bottom. So instead of throwing it up at 12 meters per second, I threw it down at 12 meters per second. It would cover that 18 meters in 1.057 seconds. I hope I've made that clear now. I've said it about 5 different ways. But you know, I don't want you to think I dropped it, because I think I misspoke there when I said that you know, I dropped it off that. No. What I actually did was, instead of throwing it up at 12 meters per second, I threw it down at 12 meters per second, and gravity helped me, and it got down there at 1.057 seconds. Okay? All right. Okay. Now, what I want to do, because I think I've answered just about all of the questions now. Oh, you know, there is one last question. I didn't actually solve this for this problem, but we can. It's, you know, pretty simple solution. You know, what is that final velocity? What's the final velocity in the y direction when it hits the ground? When hits ground. What is that final velocity? Well, you know, it's starting off at 0. And how high is it? It's at 39.94. So the final velocity in the y direction is going to be my original velocity, which was 0 meters per second, right? Plus my acceleration, which is minus 9.81 meters per second squared, times the time that it's going to get down all the way to the bottom. Now, this is from B. I really should say this, you know, so this is going to be the time from B to C, right? And so we have to figure out what that time is really going to be. We do know what the distance is, 39.94. In fact, I'm going to solve that using one of the other equations in just a second. But let's go back to this. All right, so I've got, so the time then is going to be the 3.5 seconds minus the 1.22 seconds, right? Yeah. So let me write that someplace. TBC equals 3.5 minus 1.22 seconds, right? Because it was 1.22 seconds to get to the top, and it was 3.5 seconds to go the entire route. And that leaves us with 2.28 seconds. All right, so TBC equals 2.28 seconds. So, and of course, your final velocity is going to be in the negative direction. So I'll put a negative there because it's going down. So I have 9.81 meters per second squared times 2.28 seconds. And that gives us a velocity, a final velocity of 22.37 meters per second. Right? Does everybody see how we got that? Okay. I have something. Oh, yeah. Let me see what I'm doing there. All right. Now, we've got this problem set up so that, you know, we've thrown this up at 12 meters per second. But what I want to do is I want to look at how this problem would relate to a similar problem. Let's say that I still, instead of throwing that up at 12, I'm actually going to throw it out so that I still have, when I throw it from my arm, right? Let's say that I'm a pitcher pitching for the Detroit Tigers. And I throw it, but instead I'm going to, let's just look at the velocities that I've got here. I'm still going to have 12 meter per second velocity in the y direction, but I'm going to have 16 meters per second velocity in the x direction, right? So I've got two mutually orthogonal directions there. Now together you can see this is a 3, 4, 5 triangle, so you could say that he actually threw it at 20 meters per second at an angle. I think everybody knows that if it's a 3, 4, 5 triangle, the angle theta right there is going to be 36.87 degrees. If you don't know it, then familiarize yourself with a 3, 4, 5 triangle and the angles inside a 3, 4, 5 triangle. All right, because this is my 3, that's 3 times 4, this is 4 times 4, that's 5 times 4. 3, 4, 5 triangle. And there's the angle that's inside the, triangle, 36.87. Okay, so what if he was throwing it that way? Then when we look at in the y or vertical direction, we still have this minus 9.81 meters per second squared always working on this, don't we? But what's going to be our equation of motion in the x direction? So my final distance in the x direction is going to be my original distance. Well, let's say that that was 0, right? And how about my original velocity? Now my velocity, it's still, he's now throwing it faster at that angle of 36.87 degrees, right? But it's going 16 meters per second in the x direction. Do we have anything slowing it down in the x direction like we do slowing it down in the y direction? The answer is no. No, we don't. So in the x direction, we don't have an acceleration or deceleration unless I'm, I've got a rocket that only works in the x direction or something. We could do that. Those are a lot of good questions like that too. But let's go back to this. So our velocity in the x direction, our initial velocity is 16 meters per second, right? This really is equal to 0. Oh, excuse me. That wasn't supposed to happen. I'm just going to move my calculator for a second. There we go. Okay, so 16 meters per second, right, times whatever time it is. Now, we originally knew that it's going to be in the air for 3.5 seconds, right? And then, like I said, there is 1/2, but that's times 0 meters per second squared, right, times 3.5 seconds squared. I'll do that. That's 0. And then this over here is our only thing. So how far in the x direction, if I was throwing this at this, if I had the pitcher throwing it at that direction, right? So he's going to be throwing it. Let's use another pen. So he's going to be throwing it now over in this direction. It still is going to go just as high, isn't it? But now it's also going to go over here. I'm not drawing this too well, but if I were to extend this out, it would hit over here, wouldn't it? Yes. And so now we've got two different. We've got motion in the x direction. We've got motion in the y direction. We're using our information about the y direction with, the thing going up and coming back down again to figure out how long that's going to be in the air. We know that it's going in this at a constant velocity. So 16 times 3.5 seconds gives me 56 meters. So that pitcher has thrown that ball 56 meters before it hits the ground. Now, of course, I should say pitcher because whoever it is throwing this off an 18-meter high cliff. So I don't know, maybe it's a soldier throwing a hand grenade, something like that. I don't know. But you get the general idea. So I've taken one-dimensional rectilinear motion, and now I've expanded rectilinear motion into 2 dimensions. I've also used the quadratic equation here. Everybody should be familiar with the quadratic equation. I've used the quadratic equation to solve for time, right, throughout here. Again, I think that most of this is review for most students that are in this course who have probably had this in physics in high school. And I'm just more or less, like I say, reviewing this. So where can I put those? Well, that was the best place. You're just gonna have to move, calculator. You're gonna have to stay over here. All right. So I thought that I would get actually much further with this one, but I wanted to introduce projectile motion. We haven't really got to curvilinear motion. I just want to, yeah, we got a few minutes here. So what I want to do in these last 3 minutes or so is to sort of prepare us for the next thing that we're going to look at, which is curvilinear motion. And let's just look at that for a second. Well, that didn't work out too well. This is the one I really want to use here. That's the good dark one. All right. So with curvilinear motion, let's say we've got centripetal acceleration. That's what I want to look at. Let's say that I've got motion in a circular motion. So I'm going to drop 2 radii here. And of course, this is going to be subtended by an angle, theta. Now, I've got a velocity, a tangential velocity here. So I'll call that V1. And I've got another tangential velocity here. And I'll call that V2. Now, if I was to take these two, V1 and V2, and put them together, I would have something that looked like this. Right? And in fact, this right here would be delta V. This would be V1, this would be V2, and this would be delta V, right between the two, right? I think everybody can see that. That's the same angle I have here. This would be R1, this would be R2. Now, if I was to look at these 2 different locations here, and I'll call this one A, and I'll call this one, I better use another thing that's too wide of a, I'll call this B, right? This is A, and that's B. Now I'm just going to join them with a line. I'm going to say if A and B is not an arc, but would just be a line, right? Then I can look at this triangle right here, and I could say that AB, the line AB over the radius R, is equal to this triangle over here, because remember, that angle is theta, right? AB over R is the same as delta V over V, right? If I assume that V1 equals V2 equals V, that's what I've got. I've got 2 congruent triangles, don't I? I know, back in geometry in high school, you're thinking, I'm never going to use congruent triangles. No, of course you are. Congruent triangles right here. That's where you're using them. And that's the relationship that I came up with, right? Now, let's look at what AB is. AB is just my velocity times my time, isn't it? So AB equals, let me put this, AB equals velocity times time. It's a distance. So my velocity times my time divided by r equals, and let's look at delta v. What is delta v? Well, isn't delta v just equal to v1 minus v2, right? Isn't it really v final minus v initial? Actually, I should have put it that way. V2 minus V1. It doesn't really matter. It's still delta V. So delta V is that V final minus V initial, you know, whatever, and that equals acceleration times time, doesn't it? So this equals acceleration times time. That's what delta V equals. And what is V? That's just V. So if I've got that relationship, what is that really telling me? T, I'll use the red pen. T is wiped out on both sides, isn't it? That's right. So T is gone. The V out of this can come into the numerator over here. So I've got A equals V squared over R. That's right. V squared over R. Centrifugal force. That's centripetal acceleration, but it manifests itself in centrifugal force because the force is always opposite to the acceleration, right? I mean, when you're accelerating in a car, aren't you pushed into your seat? Aren't you pushed back into your seat? Isn't the force working against the direction of acceleration? So what I've really derived here is centripetal acceleration, but of course, the force is going to work opposite to that. That's why the acceleration when you go around a corner is inward, but the force is pushing you outward. Okay? All right, well, back off to the next lecture. I hope everybody has a good idea about what it's going to be about curvilinear motion. Obviously, we're going to do some problems and stuff along that to show you how to use this information. All right, see you there.